How do you measure the change in entropy? Change in entropy, either you can measure by change in state of a system, whether it is liquid or to gas, or whether it is for the system, you can measure the entropy change by change in state, by changing number of moles of gaseous substances. Okay, but you should, while considering whether a process can happen on its own, means whether a process is spontaneous or not, you need to talk about the total entropy change of a system. A spontaneous change is the one where the total entropy is increasing. Got it? What happens, Nabila, if the total entropy change is 0? Now, total entropy is that's neither increasing nor decreasing if the total entropy change is 0. Then what can you say about the spontaneity of a chemical reaction? Is it going to happen in the forward direction? Is it going to happen in the backward direction? Or is it going to happen, Nabila, in both the direction with equal speeds?
Both the direction.
Yeah, both the direction. And suppose if 2 moles of ammonia are being formed, the 2 moles are getting reacted also. And this is the situation which is known as the situation of equilibrium. So at equilibrium, what will you say? That the total entropy change of the system is 0. Got it?
Yeah.
Right? And the system, the reaction is happening in both the direction with equal speeds, right? And but it is not proceeding net, not moving in any other direction. Okay, means it is happening in both the directions, forward and backward, with equal speeds. So there is no net change in concentrations. Okay, that's why it is known as condition for equilibrium. Suppose if the total entropy is decreasing, then the process is non-spontaneous. Means it cannot happen on its own. It cannot move on its own. Okay. You need to connect. You need to put some work. Okay. You need to put some energy to let it happen externally. On its own, it is not going to happen. That's what we had seen. And we had seen the second law. Okay. What was the second law? Who is going to tell me? Second law of thermodynamics.
Once a spontaneous reaction starts, it won't stop.
Yeah, it won't stop. Yes, and the criteria for the spontaneity also it says. The criteria is the entropy of the universe, mean total. Entropy should increase for every spontaneous change. Is it clear? That's what we had seen. We had seen total entropy is basically you need to focus on both. You need to calculate the entropy of the system. You need to calculate the entropy of the surrounding. I put the 2 arrows. One is moving up, one is going down. That is, Nabila used to tell that whether the entropy is increasing or decreasing. And the length of the arrow is telling us whether it is positive or negative. So this is positive for the system. You will be provided with the values, okay? And this is negative. And negative is more, total entropy is decreasing if you add positive and negative is more negative, okay? Got it?
Yes, sir.
So you need to focus on total entropy change. That is very important. To, uh, to know whether a system is spontaneous or not, right? And so system and surrounding, and to, to know whether the entropy of the system uh, has increased or decreased, you need to know the sign of the heat. If the heat has moved out, the surrounding have become hotter. Okay, and because they have become hotter, mean they are having more entropy. So you need to add up this. Uh, you need to add up the entropy change for the system as well as for the surrounding to get the total entropy change and to know whether the total entropy change is increasing or decreasing. So this is what we have seen. Okay. But again, we discussed that total entropy change is going to be a it is you need to keep track eye on both the system and the surroundings. So system is given, okay, or we can, it is given in the question. Surrounding entropy change can be calculated by knowing how much heat has moved to the surrounding. Heat which has entered the surrounding is the heat given by this negative of the heat given by the system. Okay. Because if system is giving heat, the surrounding are taking heat. Okay. And you write it like this. And you so you express the whole thing as minus T delta as total, and that is delta G. So now we have a new term, Gibbs free energy or Gibbs Helmholtz energy. So for a reaction to move in the forward direction, Gibbs free energy should decrease. Entropy should increase. Gibbs free energy should decrease. I gave you a parallel comparison for a ball. If it is kept on a slope, it will come down because its potential energy is decreasing in physics. But in the case of chemistry, if a reaction is there, okay, and if it is moving ahead, its Gibbs free energy change is negative, its Gibbs free energy is decreasing, then the reaction is spontaneous. Okay, this is the graph for the Gibbs free energy. So reaction, if the Gibbs free energy keep on coming down, 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 it will reaction will happen in the forward direction. If the Gibbs free energy of the reaction as per the reactant, this is graphical representation. Okay, actually you will be provided with the energy, Gibbs free energy, so you can calculate that. Okay, I have just for the sake of simplicity, Nabila, and I have shown the Gibbs free energy change as a graph. Is it clear? But actually you will be provided with the numerical values. Okay, just I have shown that if it is increasing or decreasing, I have just drawn a line like this usually. So we are going to focus from now onwards in whole of the class 12th and 11th. We are going to know whether a process can happen or not. You will say that if the Gibbs free energy is decreasing, the change in Gibbs free energy is negative, then the process can happen on its own. Gibbs free energy is a state function that we have seen. Spontaneous process Gibbs free energy decreases, and the decrease in Gibbs free energy is equal to the maximum possible useful work that can be obtained, okay, by the system. Is it clear?
Yeah.
So suppose if if that gives free energy decreasing, that energy can be used to do some work. What kind of work? Non-expansion work. Okay. Decrease in gives free energy is equal to the maximum possible useful non-expansion work obtained from the system. What is non-expansion work?
Work done with no expansion.
Yeah, example of that. So where which doesn't involve something, some gas being moved, expanding a piston. So we have seen the PV work that was related to the first one. Okay. Suppose if you are heating a gas, okay, this gas is going to expand and it is going to move this piston out. Work done, okay, by the gas equal to minus external pressure into change in volume. V final minus V initial. This is expansion work. The gas is actually, it is like that. Suppose if I'm pushing a table or something very heavy. Okay. So this is expansion work. The gas is pushing the piston. But not all kind, and this will lead to decrease in internal energy, you know. And but not all kind of work are expansion. There are certain works which are non-expansion. The example is electrical work. There are certain reactions you have seen in class 10 redox reactions, right? You put copper sulfate and zinc rod in the copper sulfate. Okay, what happens? Zinc sulfate and copper. You have studied in 10th class, right? So electron transfer is being taking place. Okay? That can be used to make a cell. So that is also work. But is it something like expansion of gases happening? No, that is just the movement of electrons. Okay, so that is
Okay.
non-expansion, right?
So
That is that
displacement reaction and non-expansion.
not displacement. Actually, redox reaction happening in a cell or a battery. They happen with the displacement, okay, and they happen with the transfer of electrons. Example, the electrical work in a cell, right? So decrease in Gibbs free energy of a system Is it clear? Non-expansion work, is it clear?
Yeah.
Okay, so how we are going to prove? Right? Nabila, I hope this is clear to you.
Yes.
Okay, so how we are going to do this, right? Delta G equal to This is the Gibbs energy change. Okay, we know that. What is the formula for delta H?
Delta H equals delta U
Yes,
plus delta NGRT.
yeah, and that was P delta V. Okay, delta H. What was the definition for delta H? Heat change at constant pressure. Okay, remember it. Enthalpy change. Heat change at constant pressure is it is equal to the heat change at constant volume delta U plus P delta V. P delta V for gases is a delta NGRT. Okay, minus T delta S. Got it?
Yes, sir.
We apply the first law. What is delta U as per the first law? Delta U equal to,
Heat plus work done.
yeah, heat plus work done. Yes, exactly. Change in internal energy is equal to the work done W plus Q, okay, plus P delta V minus T delta S, right? So we are just putting the formulas. And
Sir, shouldn't be like
delta V.
P delta.
Yeah, I made a mistake. And work done is equal to minus P external into delta V, right? This is also work done. This is expansion work. Okay. Actually, this work done includes both. Work done can be, suppose, if a chemical change is happening, it could be expansion as well as non-expansion work done. Total work. Okay. Here. So now all of these terms are, we are going to put this. And all of these terms are going to get cancelled. And we are going to end up with the work done non-expansion work. Is P external. And what is Q? What is delta is Q reversible by T. So TT is, you put this Q by T. Okay. Heat given and the temperature, the T will go is going to get cancelled. Okay. So for a reversible process, this Q and this Q will get cancelled. You are going to left with that extra work other than, if it is there, other than the non-expansion, right? In a reversible process. So this is a basic thing. Just you need to remember it. What is Gibbs energy change? It is equal to, the decrease in Gibbs energy is equal to maximum non-expansion work which a system can do. Okay. The reaction can proceed, or a redox reaction can proceed, double displacement can proceed as long as its Gibbs energy changes negative. Okay. Now we are going to come to the problem. We are going to look at both the factors of delta H and delta S in more detail. Right. Let's say, suppose if you are having, I will make a chart of it. There are different types of reaction which give heat or which take heat. Okay. So delta H for such system can be positive or negative. Similarly, we have seen the reactions where the entropy was increasing or decreasing. And we can do that system at any temperature. So what temperature will favor what kind of reaction? We are going to make a chart out of it. Suppose if delta H is negative.
But won't it be like higher the temperature, more the entropy?
Yeah, just we are going to discuss. It is not always be favorable, just we will discuss. Suppose if delta H is negative. So what does this mean, Maha?
It means the system is losing the heat. Sorry.
Yeah, losing the heat. Right, Nabila? Exothermic.
Yes, sir.
So delta H is favorable for the reaction. Means you know that the system is moving towards more stability. It is giving off heat, it is giving off energy, and the products are more stable. And suppose if entropy is increasing, that also is favorable, you know, for the system. Now we are going to look only for the system because we have expressed everything in terms of system. So such reaction can happen at what temperature? At low temperature or at high temperature or at any temperature? What is the sign of delta G?
Delta G.
Yeah, what is the sign of delta G for such reaction?
It will
Where
be negative
how you know that?
because entropy is positive, meaning
And
it will be
delta,
spontaneous.
yeah, delta is minus T delta S, right? So if you put this is negative, minus temperature, and what is delta S? Delta S is positive. So this whole term, negative, and this is also going to be negative. Negative and positive is negative, is going to be negative. Is it clear? Will are you getting a point?
Yeah.
Suppose let's say uh, example is delta H is minus 10 kilojoule per mole. Delta S is plus 10 joule per Kelvin per mole, right? So take any temperature. It is always because delta G is minus. Always don't forget to change the kilo to 10 to the power 3. 10 into 10 to the power 3. So minus temperature times delta S is 10. Got it? Delta H minus T delta S. And temperature is in, what is the unit for temperature? Kelvin. Kelvin temperature is always positive. Are you getting a point? Let's
Yeah.
say at 300 Kelvin. Let's say at 300, because Kelvin is the absolute thermodynamic scale of temperature. You have nothing negative in Kelvin. Okay, the lowest temperature is 0 Kelvin. Okay? Celsius you don't take because it can go negative. Okay, it can come down. So for thermodynamics you measure the absolute temperature, which is the lowest and which is the highest. In terms of Kelvin only you measure. So what is the delta G for this reaction at 300 Kelvin? So this is minus, this is with 4 zeros, joules, minus temperature was how much? 300, and delta S was 10. So it was equal to minus 13,000. joule per mole. Got it? Clear?
Yeah.
So at any temperature, because this is negative, and the other term is also negative. Any temperature you take, always it is going to be negative. Such reactions are spontaneous at all the temperatures. Because always delta G is going to be negative. Okay. Example is like burning of methane. Heat is released and the gaseous molecules are being formed. So it is favorable. Entropy is also increasing. Heat is going out and it can happen. Okay. Let's take another case. Second case. This is the first case. Let's talk about the second case for a reaction where the enthalpy change is negative, entropy change of the system, this is for the system, is negative. So which one do you think is favorable and which one do you think is unfavorable? Which is helping the reaction to happen and which is not helping the reaction to happen?
Delta S, because negative means non-spontaneous. No?
Yeah, delta S is negative. Yes. Overall conclusion will be drawn either from the delta S total or from delta G, because this is for the system only. Got it? Are you getting a point? Either you should get the total entropy, Nabila, for system and surrounding, you add them, or if you are just looking at the system, use delta G. That's what we have discussed in the last class and in today's uh, revision, when we have seen that instead of looking at the two different system and surrounding, take delta G total, okay, which is minus T delta S. So delta G, what is the sign for delta G? Can you tell me, both of you? Maha and
Negative.
Naveen. Negative or positive? This is delta G is equal to
Oh, sorry, positive.
uh, delta H minus T delta S, right? So the sign of delta H is negative. This is negative. Temperature is okay, doesn't matter because the temperature is always positive, right?
Yeah. Since the delta S is negative, that means delta G will be positive automatically.
Delta S is negative, right? This is negative.
Yeah.
So this is, you will be provided with the value, so don't worry about this. I'm just writing the sign. This is negative and this is negative, negative, positive. So will the total Gibbs free energy change? Will it be negative or positive? Is it always going to be negative? Is it always going to be positive? Or it can be positive, or it can be negative, or it can be zero also at some condition. Are you getting my point or not?
Yes.
Yeah. So I need to split this condition. Maha, are you getting my point?
Yeah.
If the temperature is very less, if the temperature is less, this term is going to be less because temperature is small. and minus minus is positive. So it is going to be like this. Negative delta H is going to be more than T delta S. This was negative and it was more. Delta G is negative. And the process is going to be spontaneous. Yes. Suppose if you take at a very high temperature, delta H becomes small and T delta S is small. And the sign for the T delta S is positive because negative is positive. So delta G is positive. It is non-spontaneous. Is there any certain temperature at which delta G is equal to 0? Can you tell me what is the temperature? Yeah, the temperature which is at which you can put the delta G equal to 0. Okay. And, delta H by delta S you can find out. They will give you the value. So that is the temperature. If the temperature is lower than that, delta G is positive. If the temperature is more than delta H by delta S, okay, then the delta G will positive. And the question which you were asking, you can do it in this way. Got it?
No, but sir, the problem is that we don't have delta H. We have to find the delta H, and delta U is given.
Yeah, but
So
delta U is given. Okay. The delta
yes,
U
so
is given. So you can apply the equation delta H equal to delta U plus delta NGRT.
I did, but then like I don't know what's the R. I don't know what's the temperature. Like I can only calculate delta and
And delta NG R you can take it as I told you 8.314 joule per Kelvin per mole. Temperature you can leave it as T. Okay. And you
okay.
can write
So
the
like just put the T over there.
yeah and solve the equation. You can for spontaneous delta G is less than 0 and
Okay.
solve it for T. That is the temperature. You will get your answer. Okay. I will do more
Okay.
questions today. So such reaction can be spontaneous and delta G is 0. If so delta G equal to 0, when it is going to be 0, you can find it out. If you put it 0, you can find the temperature equal to delta H upon delta S. Nabil, are you getting our point? So this is the temperature at which delta G equal to 0 and this is the temperature at which equilibrium condition. So spontaneous means it can move forward. Non-spontaneous means it will not move forward. It will move backward. It may move backward. Equilibrium means it is neither going to go in the forward nor going to go in the backward. It is going to move in both the direction with equal speeds. That is the condition for equilibrium. Is it clear or not? Right?
Yes, it's clear.
Let's take another case. What happens if the enthalpy change for the reaction is positive? And the entropy change is negative and entropy change is positive. What is the sign of delta G?
The first one will be positive.
Will it depend upon the temperature at lower temperature or at higher temperature? You need to figure out this is positive. minus temperature into negative. Are you getting the point?
Yeah.
Yes.
Navila, this is positive. Minus, so I have just applied the formula for delta G equal to delta H minus T delta S. Minus temperature
Okay.
time delta S. Delta S is negative as it is given in the question. It will be given with the values also. But here, for the sake of simplicity, I have given just a sign. Okay, you will be given with the numerical value. This is minus minus. So this was positive. And this is going to be also be positive at all the temperatures. So such reaction is always going to be non-spontaneous. At any temperature you take. Is it clear? I am talking about this case.
Yes.
Suppose if you have delta S positive and delta S positive. So can you tell me this reaction, such reactions are favorable at higher temperature or at lower temperature? Reactions with positive enthalpy change and entropy change.
Higher temperatures.
Why? They should be. They can happen at higher temperature or lower temperature. How you will decide? So just try to help me out.
Because like
Delta G sign is not
plus
given. Hmm.
delta H is even, and once the system is gaining heat, and then
Yeah.
delta S is positive, meaning high, the entropy is more, meaning spontaneity. It's a spontaneous
Yes.
reaction. So spontaneous
Hmm.
reactions, delta G will be um like
Yeah. I'm
negative,
going
right?
to put these. Yeah, I'm going to put these values in delta H minus T delta S. Yeah. Okay. So this is delta G. This is for positive value. Some positive value as it is given over here. Minus temperature times the entropy is also positive value multiplied by a temperature, and there is a negative sign. So this delta G, you want it if you want this reaction to happen on its own, the delta G should be less than 0. Delta G should be negative. When it will be negative at lower temperature or at
When the
higher
reaction
temperature?
is spontaneous, right?
No, yeah, spontaneous, but at lower temperature will it be spontaneous, or at higher temperature will it be spontaneous, or at any temperature will it be spontaneous?
Higher
Hmm? Higher temperature. Why, Nabila? Higher temperature
temperature.
because if you take the higher temperature, this value, negative value is going to be more. Okay. And it will be more than the positive value. So it will make the whole delta G negative. Higher temperature minus T delta S is more because you are multiplying with a higher value of temperature. And so that T delta S is going to be have more value, and because it has negative sign, so it will more negative than the positive delta H. So it will make the whole delta G negative. Maha, is it clear?
Yeah.
Nabila, clear or not?
Yes.
So these are splitted into different conditions. Okay. So just overall, you should remember that Gibbs free energy change should be negative. Then only the reaction can happen on its own. Is it clear or not? Right?
Yeah.
How you are going to find the Gibbs free energy change for a reaction? How you are going to find the Gibbs free energy change for a reaction?
By applying the formula.
Yes, by applying the formula delta H minus T delta S. This is one way. Or if the Gibbs free energy, just like the enthalpy of formation, the standard Gibbs free energy of the formation can be given. And with that, you can figure out what is the Gibbs free energy change for a chemical reaction. Either you will be given with delta H and T delta S. Okay. Or you will be given with the Gibbs free energy for the formation of a compound. Okay. So delta G, this is free energy change, Gibbs free energy change for a process or a reaction. And if you take standard Gibbs free energy change, just like standard delta H. Okay. Standard enthalpy change minus T delta S. Is it clear? This is the formula. Suppose if delta H and delta S not are not given. Okay. Standard Gibbs free energy change for a reaction. This is not delta H. This is delta H. For a reaction can also be calculated because a reaction is happening, so products are forming and reactants are getting consumed. Okay, so standard Gibbs free energy change for a reaction can be calculated by taking the difference of the Gibbs free energy of the formation. Okay, sum of the Gibbs free energy of the formation of products minus sum of the Gibbs free energy of the formation of reactants. This we also did in where we did it, this type of formula in delta H also.
Yeah.
Enthalpy change for a reaction is the sum of the enthalpies of the formation of products minus sum of the enthalpies of the formation of reactant. In this case, the standard Gibbs free energy change for a reaction is sum of the standard Gibbs free energy of the formation of reactants minus sum of the standard Gibbs free energy change for the products. Just like enthalpy of formation of pure elements in their standard state was taken to be zero, because everything is assumed to be formed from pure elements. Okay, you start from the pure elements. Okay, from that you calculate the compound. Okay, similarly, the standard Gibbs free energy for the formation of pure element, okay, is taken to be zero. standard gives free energy for the pure elements is assumed to. So what is the delta G naught F for hydrogen? It is the pure element. It is 0. Okay. Pure elements in their standard state. What is the
Okay, sir.
enthalpy of formation of H2O liquid? Standard state is 1 bar pressure and 25 degrees Celsius. Will it be 0? No. It will be provided in the question. It will not be 0 because it is not a pure element, it is a compound. Okay. So standard gives free energy for the formation of pure elements. Right? That is, for example, a standard gives free energy for the formation of aluminium. What is the standard state of aluminium? Is it liquid, is it gas, or is it a solid?
Solid.
Solid. Aluminium is a metal, we all know that. Aluminium foil we have seen. It is taken to this way. In its standard state. Be careful, it should not be aluminium in liquid state. That is not zero. That is not its standard state. Okay. Clear? So you will be provided with reactants and products. You will be provided with the Gibbs free energy of the formation for the reactants and for the products. You can take the difference. You take the Gibbs free energy change for the reaction, and you can predict whether a reaction is possible or not. So I hope this is clear to all. Or it can be given with delta H also. Delta H equal to delta H minus T delta S if it is given. Then you can easily know the sign, and if the sign is negative, you can make out whether the reaction is spontaneous or not. So let's do a numerical on this. I am giving you a question. Where the sulfur dioxide reacts with oxygen, giving you sulfur trioxide. At 298 Kelvin, means at 25 degrees Celsius. Standard Gibbs free energy changes. This is already given. You don't need to take the difference of the Gibbs free energy of the formation of product minus reactant. Okay, already directly given, so no need to calculate. Delta H for the reaction is given. So all these datas are given, right? You have to predict. You have to use the above data to predict if the reaction is spontaneous, at 298 Kelvin.
It is spontaneous because it's negative over there.
Yeah, and how? Yes, it is directly given. 298 standard state, 298 Kelvin 25. It is already negative. Okay, Nabil, are you getting?
Yes.
Total gift energy change is given to you, and that is at 298. And it is asking whether the reaction is spontaneous or not. Look for the sign of delta G naught. If that is negative, it is spontaneous. So this is one part of the question. I will write it here at 298 Kelvin. This reaction can happen on its own at 298 as per the given data. Okay. How the delta G naught will change with increasing temperature?
So can you repeat?
How? Next second part. And assuming delta S naught and delta S naught are constant with temperature. Is the reaction spontaneous at 900 degrees Celsius?
The reaction is spontaneous because if the temperature increases, then it means it will be more spontaneous, and then it means delta G will be negative. So
We need to look for both. Okay. At 900 degrees, if you are carrying it out. So this is clear.
yeah,
Up till this, no ifs and buts, because delta G standard if energy change is given, that is at 298 Kelvin directly, and it is asked, it is negative, so it can happen. Now the problem is that some other temperature what will happen. Okay. So suppose if you are doing this reaction, and what is being told, it is being told that the delta H and delta S for the reaction is same. Delta H is kilojoule per mole of reaction, or kilojoule, you can write one and the same thing. Means it is giving off heat. Got it? This much heat is given to the surrounding. What is the delta S of the system? For the reaction, what it is?
Constant.
And it is constant, minus 187.9. Got it? Okay. And how the total Gibbs energy change is changed, varying with the temperature. Can you tell me? It is equal to delta H minus temperature into delta S. Got it?
Yeah.
So delta H is constant, minus 198.4. Delta is Nabila, it is told that delta S is also constant. How much is it? Minus 187.9. Clear?
Yes.
And temperature, how much it is taken? This is minus, and temperature is 900. 900 is how much? Plus 273, it is 1173 calories. Clear? So at other temperature, the delta H and delta S are given constant, and you are asked to calculate the delta G at some other temperature. So put that temperature, delta H minus T delta S. Are you getting a point? Is this clear? Maha?
Yeah.
Nabila, is it clear? And just let me know whether the delta G is positive or negative. This is kilojoule. Okay. So I need to, in order to solve it, I need to multiply it with something else. So it is minus 198,400. Minus 1 is plus 1173 into 187.9. Is it clear? Good. If you add them, total they are going to have some value around 22 kilojoules. It is positive. Are you getting a point? So at other temperature, it asks delta H in delta S, you are going to put that temperature, okay, and check whether the delta G is still negative or positive at that temperature. If it is positive, then that temperature is not favorable to do that reaction. It is same what we discussed few minutes back. Delta H is negative, delta S is negative. So let's get back to our discussion. Delta H is negative, delta S is negative. So these reactions are favorable at low temperature and unfavorable at a very high temperature. And in the reaction, we have taken a higher temperature of 900 degrees Celsius. Okay, so the delta G we are getting is positive. Is it clear? Ma, is it clear? Nabila, is it clear?
Yeah.
So if you are given at any temperature, how you are going to find out, Nabila? So you are going to put the delta, you are going to take the delta H and delta S and put the temperature, find the new value of delta G, and just calculate the new value along with the sign. That is the most important, whether it is positive or negative. Is it clear?
Yeah.
So lower temperature, higher temperature. At what temperature this reaction will attain equilibrium? How you are going to calculate? Equilibrium
Secondary
means,
repeat.
yeah, at what temperature this reaction will attain equilibrium means it can happen. It will be happening in both the directions with equal speeds. You will be having SO2 reacting with oxygen to forming SO3, to form SO3.
But sir,
SO3 break.
shouldn't be the delta G equal to 0 for it to be reversible?
Yes. At what temperature? Will attain equilibrium. Equilibrium, this is a sign for the equilibrium. Okay, means half arrow in the forward, half arrow in the backward, means it is happening in both the directions with same speed, means it is not moving in any direction. That is the condition for equilibrium. So how you are going to do equilibrium condition? We know. So you are going to write at equilibrium. You are going to make it 0, right? Delta G equal to delta H. So don't write not, because this is can be any temperature, not only the temperature at the standard state. You can find the temperature equal to delta H upon delta S. This is the temperature at which delta G equal to 0. Okay. But be careful, this will be in kilojoule and this will be joule. So don't forget to multiply it by 1000. Is it clear or not?
Yeah.
So let's do one problem. And let's move on to the third law. What is the third law of thermodynamics? This is clear. This is how you are going to figure out the delta G. There is some aspect of equilibrium also. There is one more way to calculate the. So delta G for the reaction, how you can calculate? You can calculate it from the sum of the Gibbs free energy change, standard Gibbs free energy change for the products, minus sum of the standard Gibbs free energy change for the reactants. This is one way. Another way is delta H minus T delta S. One more way is this. This we are going to cover it in the chapter of chemical equilibrium. This we are not going to discuss, because this is in NCERT. It is given little bit. It is given in this chapter, but actually it is belonging to the chapter of chemical equilibrium. Is it clear or not?
Yeah. So what does log
Yes,
even mean?
Log, you know what is log?
I'm only hearing about it here in 11th. It wasn't in 10th.
Okay, log, there is a number x and this is known as base. Okay. If it is written like this, z, so y to the power z equal to x. This is what log means. Logarithm of a value is the power by which the base must be raised in order to get the numbers. Okay. For example, log 10. But normally you will not require this. This definition is mathematical definition. To the base 10. What is the value? So how much power should be given to this so that I can get this? What should be the power of the base?
1.
1. So the answer is 1.
But like,
10 to
what's
the
the
power.
point of this doing it?
Actually, you express instead of writing the actual number 100, 10,000, you are writing the powers. That is a. So, for example, log 100 is how much? What should be the power
2.
of this? Yeah, 10 to the power 2 is 100. So, normally, Nabila, you don't have to worry because in the question they give you the values. Log 100 is 2. Okay. Log 1000. This is in. So, what should be the power by which the base must be raised in order to get the number? What should be the power of 10 to get to make it
3.
1000? Okay. So these values can be directly for for 10 or multiple of 10. Okay. You need to, the value is just equal to the number of zeros. But there are certain values which will be given to you. For example, log 2. It is 0.3. Log 3. They will be provided in the question, so no need to worry as of now. Okay. Is that clear?
yeah.
Yeah.
So,
Don't worry about the log values. They will be given to you. And you can put them in the chemical equations. This is the value of delta G. Delta G equal to delta G naught plus RT ln Q. Okay. So just remember this. This we are going to discuss in detail in the chapter of chemical equilibrium. We are having this whole discussion. So don't worry about this. Okay. Now move on to the third law of thermodynamics. Okay, what is third law of thermodynamics? Can you tell me? What was second law? What was first law?
Energy cannot be created or destroyed.
Yeah. So whatever the work which you are doing, okay, whatever the heat which you are giving, that is storing in the system itself. Okay. In the form of internal energy. Okay. The energy can neither be created nor it can be destroyed. Okay. Second law was Second law, it is about it was telling that whether a reaction can happen on its own or not. So when can it happen? If the total entropy of a system is increasing. If it is increasing, the reaction can happen. It is spontaneous. Got it?
Yeah.
That was the second law. Third law is very simple. And this is also very easy to understand. We discussed one point. With that point, we can correlate that this law, how it came. Okay. So for convenience, we have taken this common value to be 0. So the third law becomes the entropy of all perfectly crystalline substances is 0 at 0 Kelvin. This is the final outcome. This is the third law. How it came? Just at the starting of this entropy part, we discussed that whenever you heat a substance, what happens to the movement of the particles? What happens to its entropy?
It'll start increasing.
Yeah, when you heat a substance, suppose if you heat a substance, if you heat a gas more, its particles will move more quickly here and there. They will vibrate more. Okay, if you heat a substance which is a solid, the particles will start vibration, and a point is attained, they may melt. Okay, the solid will melt and the particles may start moving here and there. So, Nabila, we have seen at the starting of this entropy discussion, as you increase the temperature, entropy increases. The temperature gives the energy to the particles to move them here and there. So just move in the backward direction. This is third, and this will help you to figure out what is the third law. So what will happen if you lower the temperature?
Entropy will also decrease.
Yeah, because random motions will decrease. The particles will not have energy, So they will sit quietly, okay, in one place. They will not move here and there. Moving here and there means kinetic energy that is given by the temperature by heating. So just try to move in the backward direction. If you are lowering the temperature, the entropy is going to decrease. If you
Okay,
keep on
sir.
lowering, if you keep on lowering the temperature, lower and lower, the entropy will decrease, become lower and lower. It will decrease further. And what is the value of the lowest temperature in the universe? What is the value? Yeah,
Zero Kelvin.
zero Kelvin. Kelvin is the absolute scale, right? That means there is nothing lower than zero Kelvin. Okay? Zero Kelvin. That's why we use Kelvin, okay, in thermodynamics and in chemistry. Okay. So what should be the entropy at this zero Kelvin? It is the lowest thermodynamic temperature at which all motions, all types of motion, translational motion, vibrational motion, okay, rotational motion, stop completely. They stop. Okay, so entropy will become zero. Is it clear? And when entropy will become zero, means it is the perfect ordered state. Perfect ordered state means all the particles. It is like a perfect disciplined class, okay, for a teacher, where all the students are sitting, exactly in the
So what
same.
about negative?
What about negative? Negative what? Temperature?
Negative entropy.
Negative entropy? No, entropy cannot be negative. Its change can negative. Suppose there is certain entropy in a reactant, and as the products are going to form, okay, the entropy may decrease. Is it clear?
So
Delta,
delta S can be negative.
yeah, delta S can be positive. For example, if you are having carbon monoxide and oxygen gas 1.5 or like 2 moles of carbon monoxide, 1 mole of oxygen reacting to form 2 moles of CO2. What is the change in entropy? Sign of change in entropy. Positive or negative? This is gas. This is gas. How many moles of gases were there in the beginning? 3. And how many moles were there in the product? 2. So entropy has decreased due to chemical change. I'm telling, in this
So
case,
it
I'm
needs to be 2O2, no?
you know 4 oxygen are there,
Oh yes, sorry.
2
4 O2.
and 2 carbon, right? 4 oxygen atoms and 2 carbon atoms. 2 oxygen here, 2 oxygen atoms here, and 2 into 2 is 4 oxygen atoms. Is it clear? Or write
Yeah,
it
but
like
I'm
this.
saying that in front of O2 it should be 4, no? For
No,
balancing.
no. It is already balanced. Or look it like this. Nabila, are you getting? Is it balanced or not? What do you feel? Is it
Getting.
So you have carbon monoxide and half O2 means how many atoms of oxygen? Half O2 means
0.5.
0.5 moles of O2. So how many oxygen atoms? Half into 2, 1. Getting my point or not?
Okay.
1 oxygen atom, CO, and you are going to have 1 oxygen atom being added to it. So total entropy change If the entropy, whatever is there, if it is becoming more, it is positive. If it's becoming less, it is negative. Okay. But at 0 Kelvin, what is the entropy of any substance, pure substance? That is 0. Because just imagine everything started from 0 Kelvin. Okay. So 0 Kelvin, all the things were in perfect crystalline form where all the atoms were perfectly arranged. Okay. And as the temperature increases and as you come to the room temperature, some of the material melt and change to gas. So that definitely, or some of the material may remain in liquid like water. At room temperature, it becomes liquid.
Okay.
But its entropy has increased. So third law is at 0 Kelvin, you work backward, you think backward. 0 Kelvin, there was no motion, there was no energy at all. So all the particles were sitting in a systematic manner. Okay, the entropy value of any substance, perfect pure crystalline substance. Crystalline means all the particles are arranged in a perfect manner. It is just like a class where all the students sit in the same posture, exactly straight line. Does that happen? And all have same type of pens, all have same type of notebooks. They are taking their notebook out at the same time. That doesn't happen. Okay, they are is sitting exactly in the same line. Okay, and not doing any talking to each other. Okay, that doesn't happen. There is a lot of entropy in the class. Okay, everybody sometimes they start talking as the teacher goes, and right. So imagine molecules also like that. So if you take the 0 Kelvin temperature, all the motion will stop. All the particles will be arranged in a systematic manner. Okay, and you will have a perfect crystalline substance. Okay, normally you don't find such substance because that is just a theoretical, because that temperature is very difficult to attain. It is there, it is found in universe where you do not have any energy. Okay, so there the entropy of that particular pure substance is going to be 0. So clear, this is the third. And
Yes.
as you are increasing the temperature, the entropy is increasing with the increase in temperature. But in a chemical reaction, due to change in state, the entropy may increase or decrease. Okay. So this completes thermodynamics and thermochemistry chapter. Next, we are going to start with atomic structure. Very important chapter. And it is going to form the basis of electronic configurations, which are going to be used in whole chemistry. Okay, so next chapter will be atomic structure. Okay, so let me end today's class. Okay,
Thank you, sir.
bye bye, good night, take care.
Thank you, sir.